Okay. So thank you for the introduction. I'm Orri from Meta, and it's really exciting to be here to see how Velox is going places. And of course, we have this distinguished lineup of practitioners of the true science this morning. So we'll be hearing lots of bold claims about 10x and more. And of course, what would Velox be if Velox was not an integral part of this exciting inflection of our industry? So I'm going to be talking about a bunch of things here. So first we will just acknowledge the fact of the matter that hardware renaissance is here. If there's a way forward, this way does involve specialized hardware and next-gen architectures of different sorts. So specialization has arrived. And then we'll be talking a little bit about what actually we would be accelerating if we were accelerating the typical Velox workloads. Then we're going to be talking a little bit about GPUs, like how they work and what's different about this next generation architecture. Mostly GPUs, but some of that stuff is going to apply also to other kinds of devices. So then if Velox had a charter, then what would be the charter of Velox Wave? I mean, we pursue some of the same values, but it's a different inflection, so we call out slightly different things. So we're going to have a world of heterogeneity. Even now we do have, even if we don't have that many vendors in that space, there's still going to be differences between models. So how do we tackle that? How do we adapt to a pretty wide range of different capabilities on which we're going to be running? Then supporting work streams in specific benchmarking, how we have a nascent race going. I mean, there's people gathering, on the starting blocks. So how are we going to measure success? Is it going to be TPCH? Well, that's what it is now, but can it be better? Yes. So file formats, how do we represent data? After all, it's all data. So can we do it better? There's a wide ranging nascent consensus, yes. So, and then finally, what we're going to do and how are we going to try to bring these many streams together that people are initiating all over the place to, climb this exciting mountain of data. So, okay, so the next place. So we are always asking ourselves, what's ahead? And it has seemed for the longest time. I mean, people have been predicting the demise of Moore's law, and it seems to have arrived, certainly on the CPU side. So the out-of-order execution field has kind of been raised dry. There's a little bit of one instruction extra occasionally from generation to generation. So that cake's been eaten, more or less. So there's some of that same dynamic is surviving. Moore's law keeps getting longer in the domain of accelerators and in the domain of networks, where we still see like 2x generation over generation improvement. The generation is about 2-3 years or something like that. So there's more forward momentum. And of course, if we look to how we continue to tackle growing data, we're going to have to look in that direction. So what drives this? I mean, it may be that some of the initial impulse of our technologies, internet protocols and stuff like that came from defense and the classified world. But as far as we can tell, for the longest time, we've been having consumer applications are driving the demand. So the internet was arguably the birth of the high-performance cluster. Certainly, the hyperscaler data center was a product of the internet. So the server-side development is like this. The client-side development is graphics, gaming. Gaming gave birth to graphics, and gaming gave birth to GPU, which is the first instance of like throughput-first type processing. You do the same thing on a lot of data. And occasionally that happens to work also for AI. And then AI became a big thing by recommender systems and other such things. I mean, advertising on one side and the feeds on the other side, the two big applications at Meta and Google is not much different. And then kind of once this thing came into being, the conditions were created for the emergence of large language models and chatbots and stuff like that. But these would never have come unless the critical mass had been reached by precursor applications. So this is all a fact on the ground. Meta is a big consumer of NVIDIA. We have lots of GPUs and we're buying constantly more. So these are certainly in training, they're very mainstream. Google for the longest time has been making its own silicon in that space. So these are things that are in somewhat specialized applications in the data center, but what we're going to be seeing now is how this type of technology, maybe in a slightly different configuration, is going to make AI go everywhere. So acceleration goes everywhere, accelerates data, and if so, then it becomes also convenient to run inference wherever you're running data. Or maybe even little training, so you'll have like a training and inference as aggregate functions in SQL queries, that sort of thing. These things don't have to be isolated silos. They are that often, but they don't have to be that. So there's a way to go, even before getting into the sci-fi stuff like superconducting. That's known to work, and it will consume less power, but it's a lot of hassle. So that hassle turns out not to be necessary. We can have another 10x and maybe a next 10x even before we have to go there. Optical quantum stuff like that is more speculative. I mean, eventually we might get there, but we don't have to get there to have excitement, because we got excitement in room temp silicon right here. Okay, so the next slide. Okay, we already went over this. The hardware has arrived. Hardware has arrived, yes. Software has traditionally lagged behind. For those who remember history, it was the longest time that you had 32-bit PCs on every desk, but the operating system was 16-bit Windows. So the switch from 32 to 64-bit was a bit smoother. You did not have to like re-architect everything. It just was wider, and that took some time. That took years for 64-bit operating systems and applications to be universal. So software tends to lag behind. In our particular domain of accelerated data, there's been for the longest time one of Blazing SQL, of course, and the grandfather of us all, Rapids. Those things have existed for a while. But they have not been like a mass movement to date. It's been, academic systems have existed in that space. There's been proof of concept. Generally, there's been the sentiment that the next gen of hardware is going to make this a breakthrough case. And arguably, the next gen hardware is here, is the software. The software is getting there. And of course, we'll have to see as a community what we're going to do about it and how we can accelerate this, the landing of this acceleration. Okay, so data management runs the world. There's nothing that works without, but data management has not been driving the hardware. Hardware has been, as far as we can tell, been driven by big consumer applications, so both client side as well as data center side. So, but we have an exciting time. The stage is being set. So a few more things, but let's look at the situation at Meta. So we have Velox. Velox is giving 2 to 3x. Typically, if you can compute 3 times more in the same space, and you're going to compute 3 times more, you're not going to give up the capacity that you have. You're just going to make more use of it. You just run more queries if you can run more queries. There's like a constant appetite for that. So experience seems to confirm. So Velox, if you look at Velox on a good day, it's pretty good for what it is, the vectorized execution on CPU. It's not obvious there's like a systemic failure in there that by eliminating which you can do 2x better. If you can do a lot better in certain cases, and there are cases that are like silly errors, then these errors have been fixed. And what we've been doing for the past, since VLDB, where we last talked about acceleration, we've been mostly fixing Velox batch. So instead of working on acceleration, but it's okay because we need to get to the show on the road, and the show has to hit the data center floor. And now this process of productionizing Velox has its own momentum. It's being done. It's getting there. People know how to do it. So now we have a little bit more breathing space to look into the future and see what's our next revolution. I mean, we cannot stay where we are. I mean, if you stay in place, you're going to be moving backwards. The world keeps moving, and the Velox has to continue leading in this space as best we can. So what kind of proposition? Another 3x. Can we get that? Where can we get that? Can we get it from query optimization? Well, in some cases we can, but not across the board. Query optimization traditionally does not play a ton of role with hyperscalers. Just if you have a data pipeline that's really important or a workload that's really important, it tends to be very repetitive, and then the application owner does whatever it takes to make that run more or less efficiently by whatever means. You know, special flags, special session properties, special configs, special everything. So typically little trust for query optimization in that domain, which means that the big applications don't really have a ton of upside from query optimization, and they're kind of making reasonable things. If you had tons better query optimization, maybe you'd have less intermediates and more joins and things like that. But customers are doing their thing, and what the customers are doing is what we get to accelerate. So that's the fact on the ground. Systemic failures in Velox, there's no 2x in there. We'll look in the next slide into that more. So can we then, by re-architecting around accelerators, can we get a multiplier of, the best case multiplier of 10x, average a multiplier of 5x? With today's low-cost hardware, we shall see. In some cases, we know that we can do that. How generalizable are those cases? And do they match a representative proxy of our workload is the thing to find out, and we're engaged in finding this out. So then suppose next year comes and we have a proposition where there's like a new data center upgrade. I mean, data centers keep changing. More equipment gets phased out and equipment comes in at a regular pace. So if we have then this point of choice, what kind of equipment are we going to introduce then? And then we can say there's an accelerated configuration that gives for the same floor space and same price is going to give 5x the processing, then that might be an appealing proposition. We shall see. Okay, so what is there to be accelerated? So we look at a bunch of Velox CPU. We see what's it doing. It's a lot of the standard decompression and a little bit less compression. Some, as you would expect, decoding columns. It's not like TPCH where hash join is the dominant operation and repartition is after that. Here it's more table scan and lots of encoding, decoding, decompression, encryption for SSL, because we have to have data encrypted in flight, even in the data center. Turns out to be quite a bit consumer. So decompression and encryption, decryption are kind of good candidates for acceleration. And then, of course, decoding table formats, file formats is a well-known one. Hash join is kind of the killer application, but hash join is not very big in our workloads, unfortunately. So then, and there's a long tail of everything. And if you're going to have acceleration, then you better have acceleration across the board, because it would be hard to justify otherwise. So by the operator, you move from looking at self-times of CPU functions to operators. Table scan dominates. Repartition is big. Understandably, if you do shuffle the data all the time, there is no single node application. Cluster sizes are several hundred nodes. We can move sometimes from Java, 1,000 node clusters, 1,000 little servers of 64 gig and a single Xeon chip. We can move maybe to 400 or so in cases, 600 in cases, 500 in other cases. So we can go to smaller clusters, but clusters, they still have a significant count of machines, certainly in the mid-hundreds. So repartition is understandably large. Then writing tables is big. Aggregation is bigger than hash join, and hash join is not very large, like 6% or so. Miscellaneous expressions, when they're not broken, expressions can be extremely high if you got some function that's silly, inefficient, but when they work, expression evaluation is not very high, it's like 10%. So this is the sort of bread and butter of which we're gonna have to eliminate like 4/5 or something in that ballpark. Okay. So platform utilization, of course, if you're not using CPU, why would you optimize it? You can keep adding queries to Presto clusters, Prestissimo clusters, and CPU utilization will go up. You can hit 100%. And it's to be remembered that from 50% to 100%, you get maybe 15% throughput. Because when you're running at 50%, every core has one thread busy, and then when you add the other thread to these double-threaded cores, you get double CPU utilization, but you don't get that much throughput, 15% or something like that. So that's to be remembered when interpreting these things, and over 50% is very easily achievable. And when this is achieved, network utilization tends to be at like 30%, a quarter, a third, something in that ballpark. So we are not network bound, which is kind of surprising. And so if CPU operations cost absolutely nothing, there is a point to be made that things would have a wall time that would be about 3x less. So there is some upside to eliminating CPU work. Of course, if you move to a next generation of data center gear, then you'll also get a new network. And the network that we're talking about here is like a 12.5 gigabit per small server. So it's a 50 gigabit interface for every 4 small servers, and these 4 small servers have like 20 cores of Xeon and 64 gig of RAM. So lots of small servers. Okay. So at high concurrency, we are CPU bound, and therefore eliminating processing cost is significant for us. Okay. So compute, what is compute? That's a philosophical question. Map and reduce are mathematical concepts that were embodied in a programming language for the first time when it was Lisp, and then Lisp never became a big thing, but all the things that were pioneered there did migrate to mainstream. Automatic memory management, lambdas, functional programming, all of that found its place in the current mainstream. Map reduce, of course, these words currently will evoke the image of Hadoop and Google's clusters, and basically lots of very heavy, high latency processing. And us database people have always kind of looked at like it's funny, like, hey guy, have you forgotten 50 years of database? Stonebreaker asks indignantly. And okay, what I would think back in the day would be, okay, fine, if nobody knows how to do query and you got a ton of data and you must get it processed somehow and you have like infinite manpower to write these things by hand, then MapReduce must be the only thing that you can do. But okay, there is some justification to organizing compute, because compute in many applications organically does kind of resolve into these notion of running something on everything and then adding them up in some way. So in this case, for the case of data management, table scan, filter, project join is the map side, where typically you can process every value independently and you can process as many at a time as the platform will do. And then you got reductions, which are aggregation when you add them up. Repartition is also kind of reduction, because when you generate data that you split between multiple outputs here, what you put there depends on what you already have there. Same thing, file writing is another form of reduction, where you have to look at all the values to decide how you're going to encode them. So you have value-to-value dependency. Of course, in other applications, HPC, ML training, you have everybody trained separately. Then there's a reduction where you add up the connection weights from everybody, and then you broadcast them to everybody else, and then you keep training separately. That's how PyTorch works in many cases, in the recommender cases, for example. Sometimes you have distributed training that's not deterministic, where these training nodes exchange data on a peer-by-peer, like group by style. Everybody talks to everybody else. So you have different patterns of that. But again, it's a pattern of compute in isolation and then exchange. Simulation, HPC, graph analytics typically consist of supersteps. You divide the world into little cubes, and you have certain metrics like temperatures and pressures and or what have you, measures for these cubes, and then you add up your neighbors, that's a reduction, and then you broadcast to all neighbors, that's a map. So these processing types are kind of universal. What's special about data, however, is that, okay, if you think of weather, or if you think of aerodynamic airflow around an airframe, how many measures do you have per little cube? I mean, I don't know how many exactly, but it's not going to be 20,000. Whereas in data management, you have 20,000 dimensions for machine learning, and you do something different for each dimension, typically independent of the other dimensions. Your data sizes will be skewed, your distributions will be skewed, it's going to be more dynamic, it's going to be more decisions to be made for smaller units of data processing, more branchy, and therefore less parallelizable, harder to parallelize, harder to use massive bulk processing. And of course, the supercomputer architectures and GPUs and all that have evolved for the situation where you do the exact same operation on billions and billions of items in a cluster. So data management has some extra challenges for using that kind of platform. So there are a few words about the characteristic of our new platform. So first, if you have an accelerator, you have to feed it. Now, PCIe 4, 16x, which is kind of common, is going to transfer up to 24 gigabytes per second from CPU memory or NVMe or network, as the case may be. If everything is perfectly staged and the best case and the big chunks of transfer is going to transfer about that much into the accelerator. So whatever you can do at incoming data rate of 24 gigabytes is good, because then you're going to be bounded by that, and then you have to do whatever it is you're doing at that incoming data rate. And what can you do? Well, depending on the model, you have internal memory bandwidths in GPUs from 600 gigabytes per second to 3 terabytes per second. Again, these are best case numbers. So if you do coalesced data transfers on consecutive addresses, you get very high memory speeds. So for every byte that you move into the thing, as long as you move it in chunks of several megabytes, you can afford maybe 10 round trips between the processor and its memory, and you can still keep in the budget of consuming data at this incoming rate. So that is kind of good news. So it works well if you have a few round trips. Then as a point of comparison, you can say that memcopy on mid-range CPU, if you have the best absolute memcopy where you have every thread doing memcopy and you do big memcopies, a gigabyte size memcopies, you get throughputs of maybe 40 gigabytes per second. Now, the other night, the glorious hero of column stores, Peter Bunch, the king of Amsterdam, told me the other night that, hey, Orri, don't betray the true faith. You do not go comparing yourself to memcopy, because memcopy is for losers and wimps. They compare themselves to memcopy. The tough guys, they compare themselves to cache throughput. So there is some merit to this statement, but cache in CPUs is certainly important, and you can run vectorized engines more or less in cache on a very good day. On accelerators, typically you don't have cache, you don't have tens of kilobytes of L1 per thread and not megabytes of L3. You do have a few bytes of L1 and you have some tens or hundreds of bytes of L2. So these things are kind of built to be missing cache, and they're missing cache all the time. So you cannot really count on cache, but you can, of course, reserve what's called shared memory, and which has its own downside. So what are the catches? We have this awesome platform that's going to run 10,000 operations all at the same time, as long as more or less you do the same thing on every data item. But it's not quite that simple, because it can run 10,000 or 16,000 wide only if what you do is something really trivial. The more complicated your thing is, the less parallelism you get because of a thing called register pressure, or if you need to allocate fast memory for these lanes to talk to each other, called shared memory, you only have so much of that, and the more you consume, the fewer threads you're going to be running. And of course, these kernels, there is a kernel, is this little piece of program that you launch on a device like that. Launching a kernel has an overhead. So suppose you do the worst thing that you can do on a GPU is you copy 1 kilobyte into the device, you compute on 1 kilobyte, you copy that kilobyte back to the host, and you enqueue these 3 operations in a stream, and then you wait for the thing to finish in a 4th operation. That's like sync the stream. You can do these things at a rate of something like 30 microseconds, 30 to 40 microseconds for the whole shebang, and then you repeat and another 30 microseconds. And of course, the data throughput is kind of sucks. So you cannot do that. You can do that on many threads, and then your throughput is going to be higher, but it's still very, very bad. So you got to be transferring megabyte-sized things, and you got to have your whatever it is you do it's got to take like tens of microseconds at the very least. Otherwise, you're going to be losing because you have latency. Even when you have two things queued up, one kernel finishes and the next is queued up ready to run, it's going to be like 4 microseconds for it to switch. And during these 4 microseconds, every one of these 10,000 lanes can do like 4,000 instructions about. So 4,000 instructions times 10,000 lanes is going to go up in smoke every time you switch from kernel to kernel. So you got to be careful about this, otherwise you're going to lose your edge. So, but all the same, there are some very, very good cases where they do produce a lot of wins. More problems in this line of work is that you'd have no portability of operators. Essentially, repartition, hash join, table scan, they're kind of, they may look a little bit the same, but they're fundamentally quite different. Is there some portability on UDFs? Well, for the simple ones, maybe. If you can express it with our simple function interface, where you basically run like one scalar operation, you express one scalar operation, so then you can run lots of these scalar operations on parallel lanes, and maybe you can reuse some of that code. You got special functions like maps and reduces, and second order functions like transforming or reducing or distinct of an array or things like that. Forget it. You gotta write them special for the platform. Memory allocation, don't do memory allocation on device even if you can, because your performance goes out the door. So you gotta be doing it like a three-staged memory. All memory staging decisions are on the CPU, and all the data movement and data compute is on the GPU. And don't sync too often, because every time you sync, you're going to be like throwing millions and tens of millions of instructions up in smoke. So stay on the platform and don't move data back and forth. So if you can live within these restrictions, you do have occasional 10x's or 100x's in special places. Okay, so thread. This word is being used in two completely different meanings. If you talk about CPU vectorized execution, you spend a little time deciding what you're going to do, and then you keep doing it for 1,000 values or 10,000 values. You keep doing your thing, and it's kind of nice because while you're doing your thing, you can get a couple of iterations of the loop at the same time because of out-of-order execution. And prefetching will trigger automatically, typically, or sometimes you can trigger it explicitly, and it will help you. And then once you're done with one loop, you decide what your next loop's going to be. And you can, without too much trouble, you can have iterations of the loop that depend on the previous iteration. And then you spend a little bit time deciding, and then you loop again, and you end up 95% of your time in these tight loops, and it's all very good, and it's a good fit for the CPU. So the GPU is different because no longer do you have like a thread, and the thread does loops. What you rather have is you have a so-called thread, which is quite a different type of thread, but you got one per every element of your vector. So then you better hope all the vectors are the same size, and it doesn't take very long to decide what's your next action. You decide, you operate on one element, decide, operate on the next element. Maybe you can operate on a few elements at a time, or a few elements in sequence. Typically, it works well if the elements you operate on are in consecutive places in memory. That tends to be more efficient than if they're scattered all over the place. Maybe you can carry some things in specially allocated L1 cache called shared memory, but the more you use that, the less wide you run, so there's a trade-off there. So these are the differences. So Wave, if we look at Velox, Velox started as an idea of converging vectorized execution. So you take the best of breed vectorized execution, you do all the operators, you do all the functions, everybody uses it, you get converged semantics. Everything means the same thing on all compute platforms because they share an underlying implementation. And then you can also, if you do carefully work with memory like Mang described to you yesterday, you can hope to run in a fixed memory envelope and be reliable even at high utilization. And these promises are being by and large realized. So it's coming together. So then what is then Wave? Wave on top of this is the idea of uploading entire plans. So you have a Velox plan, you want to offload the whole thing, because if you don't, you're going to be gated by device to CPU transfers and latencies of synchronization and stuff like that. So better queue it up from table scan all the way to the repartitioning. Typically, the fragment has always table scan in front, sometimes exchange if you're reading from a previous fragment. And then it's got some projection expressions. It quite often has intermediate aggregation over table scan, and if it's over an exchange, it's got final aggregation quite often. And then it's got another repartitioning at the end. So this is a typical fragment. It occurs all the time, and the whole shebang should be offloaded. And then the CPU is just going to be waiting for things to happen and making very quick decisions about what's the next thing going to be. And oftentimes it should not stop, to wait for this thing before it launches the next thing. It should just keep every queue full all the time. And then if you keep all queues full all the time, then the device is going to run things in order of memory arrival, more or less. And you'll have, generally speaking, high platform utilization. The point of massively parallel devices is you got to give them a lot of work and let them figure out in what order they run it, and you'll have, on the average, good outcomes. Okay. So then the other thing that was special to us is we have to be running on really wide data, so 20,000 columns. Each one has a different operation, must work. So it means you have few rows, but you have many columns. The columns are typically data independent, so you can maybe queue up all the columns independently. But then if you queue up all the columns independently and you have a next operation that depends on 2 columns, then you must have a barrier to synchronize that the 2 columns you depend on already. And this barrier is, again, the dreaded kernel border, where you lose so many instructions just for the pleasure of syncing. So this is the model. So the implications of running on an accelerator are, of course, that running in fixed memory is no longer like an aspirational goal. It is an operational necessity. And the other thing is that skew mitigation is not a nice to have, but it's, again, an operational necessity, because heaven forbid you have 1 billion values in your hash table, and one of these billion values happens to be half the count of either probes or updates. Then you're going to lose like there's no tomorrow. You'll lose flat out against the CPU, and you must never lose. You got to win 10x most of the time, and sometimes you break even. But losing by 100x, even in outlier conditions, which skew may very well generate, is not an option. So you have to make these goals explicit. And then, of course, you have lots of little loops, different kernels, different special things. CAB is a wonderful thing from NVIDIA that has very nice implementations of many common operations. But CAB does not do every operation. There's more in the data space. Of course, Rapids has more of this style of thing. Are these the definitively best implementation? Well, you don't know. There's no way to know unless you try doing something better yourself. So we recognize a huge space of optimization. We have lots of variables to tune, and lots of space for very specialized innovation. So Wave should be a framework where this specialized innovation can flexibly be plugged in. So then, okay, trade-offs, compute model, we talked a little bit about that. So the thing is, even if your memory is 10 times faster plus, you have 1/10 of the memory you would have. The high-end, the expensive GPUs have like a 96 maybe for H100, 80 for A100. Some Intel things, I think, have 128 gig. But it's a fraction of what you have in CPU memory. And so what you want to do with that memory is you want to have these queries go in and out very fast. You don't want to have lots of queries consuming memory at the same time. And maybe later today we're going to have Compute.ai tell us about memory and how we misunderstand memory. As far as I understood, we think that spilling is a calamity and a rare outlier, whereas spilling ought to be a way of life. And so maybe with GPUs, we will find that spilling, at least to CPU memory, is going to be a way of life. And we have to build the things so that they can and will spill all the time. But rather than spilling, we would just have fewer queries at a time and move out very fast. But then you're kind of tying yourself to optimizing wall time. which is tricky in a distributed system because oftentimes you'll be running at the speed of the slowest node. So there's some of these questions exist. Yeah. Okay. So then some techniques that we plan to do for repartitioning, and you'll see. I mean, the interested will see that in Velox open source in due time. Okay. So experience so far, the complexity tends to be in what we have experimented with. The complexity tends to be more on the control plane. The device side things, they're repurposing some cub PCs. They may be repurposing some rapid species in the future. We have to be playing a bit. We have to get a bit more experience so we know the laws of physics that apply in this particular place in the universe. And these laws of physics are somewhat different from those that apply on the CPU. So we shall see. But there's a fair grasp of this general kind of problem. Okay. So tons of runnable threads. Have lots of things ready to run and something will happen. Okay, CodeGen. Our heroes of the AJNC agree with us that CodeGen might be more trouble than worth. If we might CodeGen PTX, this NVIDIA assembly, if that's the absolutely only way to win, but we don't think it is. We don't think it will come to that, because if instructions are for free, you can, whether you run between memory access 10 instructions or 100 instructions, it doesn't particularly matter. So CodeGen as a last resort, not as a first choice. Okay. New problem. So moving data around, and sometimes you have to move data around because you don't have too much memory on the device, so it could happen. We maybe have to build to spill. So then, validating the vision. So we take something that's like an RTX 4500, which has a retail price of $1,000 there on either side, and then we take a $300 CPU. We put $800 worth of NVMe, $1,000 worth of RAM, and then we get something with a ticket price of 3,200 or something like that in single quantity retail, and we try that and we run some representative thing of our workload, which is not going to be TPCH, it's going to be like complex types, complex aggregation, not something you can do with atomics like count and sum, but more like approx percentile, distinct sets, max buys with top Ks and things of that sort. And then if we got a killer multiplier with this, then we're playing. The future landscape, generally, you got to be more and more planful if you're going to be chasing performance, because latencies don't get any better. Throughput continues to double. From PCI generation to the next PCIe generation, it doubles, and the network throughputs likewise. The data center is going to be more configurable. The chiplet models, it's going to be more like a motherboard than a rack. And then you might have a very different interconnects at different distances. And so however will you optimize for a thing like that that keeps moving and is configurable and quite heterogeneous? So some ideas for that are, okay, for different chips, you have to just measure things. You have to measure throughputs and latencies for the different operations. And then you're going to know, you're going to have grounds to decide how many of these will you run at a time. Will you fuse these operations in a kernel? Or does it make sense to pay for the kernel switch if these operations run at significantly different widths? I mean, there will be examples on either side. And it might depend on the architecture as well as properties of the data. So there's going to be a lot of space for adaptivity. And you just don't know this stuff until you try. So these systems have to be built around the notion of trying and adapting to the particular characteristics of the platform and the data, probably. Okay. Benchmarks. So we have like all these racers want to race, but the racetrack is TPCH for lack of anything better. Okay, TPCH is not all bad because the things that occur there do also occur on the shop floor. But the problem is they occur in entirely different proportions with entirely different widths, entirely different data distributions, entirely different data types. So TPCH represented the sunniest day of data processing. All the bugs that Jimmy was talking about yesterday that we have optimized for, none of these would have been hit with TPCH. And all of them have been hit with real workloads. So optimizing for TPCH is not a very good predictor of real world workloads. But it's something, and it is well accepted. So we should, I'm a great fan of TPCH. Back in the day, I made one of the best implementations with OpenLink Virtuoso, so like 10 years ago. So TPCH is well known and loved, but it does not particularly correspond to reality. What would correspond to reality is something we're working on with Intel and MIT and other people who are into benchmarks. And this would be like a remake of TPCDS where we add like feature engineering type things where we have 20,000 features that you extract from that and you prepare, cook them up for machine learning and test the data sets and stuff like that. And maybe this benchmark might be a better fit, like an AI first type fit for evaluating the data management that's going to be feeding this AI. So we're working on that. It's no secret. Okay, the other thing is our glorious file format club. So the all-stars repertoire, Parquet author Wes McKinney as our editor, and participants like CWI from Amsterdam and Carnegie Mellon with famous legendary Andy Pavlov, and Meta, of course, Microsoft, Voltron. Many people agree, Tsinghua University, people agree that Parquet might not be the ticket. Although Parquet kind of performs a function, nobody says different, but can it be better? Yes, it can be better because you can support parallelism a lot better. You can be much more SIMD or accelerator friendly in these data layouts. And there seems to be kind of a readiness to move on from Parquet. And so right now, the first deliverable we have, of course, Alpha, or Nimble as it's called now. You'll be hearing about it in another talk today, which may be kind of the starting point for the file format club. The initial deliverable being like a reference implementation that has metadata all in place, and then you can play with plugging in your own encodings and stuff like that, because encodings are a vibrant research community. We have lots of work. CWI has produced ALP, FSST, fast lanes. The Munich guys have made beta blocks and so on. So there's active work there. And this active work needs a forum, and we have a forum, and we have a platform. And of course, Wave hopefully will provide also GPU implementations, or a place where you can plug GPU implementations of all these things. So we'll learn. Okay. So developing in Velox finally. Well, Velox has a lot of stuff in place, and Velox has tests, and Velox has a CPU fallback for everything. Like also the Voltron guys with Theseus are using this. So Velox is certainly an enabling factor for going to the next gen. We're engaged in that. Right now, what we have out there is pretty rudimentary, doesn't do very much. So we will be significantly beefing it up so you can actually run meaningful plans. And we hope to be, as soon as possible, offering some relatively stable APIs where you can plug in your kernels. And then we do know of many like research results, for example, that we'd like to test in this platform. We'd like to incorporate them. But before it makes sense to incorporate, you got to have like somewhat stable APIs and somewhat stable scheduling, somewhat stable description of what these kernels do and how they want to be scheduled. And like this, we can open the gates to like more collective innovation in this space. It's very large, complicated, idiosyncratic design space, which is this space of accelerating compute. So with these, a little over time, but I hope it's been worth it. So exciting times, and we'll see everybody on the racetrack.
Is Wave a generic interface for all types of accelerators, or is it specific to GPU?
Well, right now we develop in CUDA because it does have an environment, and it has tooling and stuff like that. So it's by far the best way to approach this domain. having said this, your next talk you're going to be hearing about FPGA work from our friends at Neuroblade. So they have a Velox integration that does not run with Wave, because what they want is just to take the whole fragment of LAN and just run it their own way without any of this coordination. So Wave is more something, let's put it this way, the target of Wave is something where you can run single instruction multi-threaded programs. So this does not mean NVIDIA exclusively. It could mean that you could target FPGAs with Wave using SYCL, which reportedly has a way of generating FPGA code from single instruction multi-threaded programs. They look a little bit like early generation CUDA. And we are not very deep into CUDA specifics, so it's pretty plain CUDA. We don't do a lot of these consumer producer models or cooperative groups or this more fancy stuff. So we think we would be portable to many things that take some kind of single instruction multi-threaded programs. And so it's to be seen. There's language side work. Of course, Microsoft reportedly has some language side work that would also be capable of targeting FPGAs. The Triton language hopes to simplify making massively parallel algorithms. And so we can see other types of targets, but right now the most actionable target, or the most readily available, or maybe the most broadly adoptable target at this time seems to be the CUDA GPU.
Thank you.